Right now, something is happening in the universe that none of us can directly feel. The distance between distant galaxies is increasing a little more every second. Space itself is stretching, as if being slowly pulled by an invisible hand. But the truly strange part is the instinctive question this expansion raises. What is the universe expanding into? Is it spreading into some kind of empty void, growing into something larger that surrounds it, or has the very idea of an outside been an illusion from the beginning? In this video, we're going after exactly this question, the one that breaks our everyday intuitions. You'll see, step by step, that the universe isn't expanding outward like a balloon into some pre-existing space. As it grows, it also brings into being what we casually call the outside. So get your mind ready for the possibility that what you're about to hear might permanently change the way you look at the universe. Because this journey will challenge not only how space expands, but also how you understand what we call reality itself. Picture a balloon expanding in the room you're sitting in. As you blow air into it, the rubber surface stretches outward and pushes the surrounding air aside to make space for itself. The balloon grows because there's already a space for it to grow into. Your room provides that space. This feels completely logical to us. In our everyday experience, expansion works exactly like this. But the universe gently smiles at our logic. When cosmologists say the universe is expanding, your mind instantly imagines that balloon. You picture space pushing outward into some vast cosmic room, some enormous emptiness just waiting to be filled. You assume there must be a boundary where our universe ends and something else begins. This way of thinking feels natural, even obvious, and it's exactly here that physics shatters our comforting assumptions. The universe is not like that balloon. When space expands, it doesn't push anything aside. There is no cosmic living room, no container, no outside. As the universe grows, it creates the very thing we call space along with it. Think of it like this. Imagine trying to draw a circle on a sheet of paper that's bigger than the paper itself. That's impossible. But instead of grabbing a bigger sheet, imagine the paper itself magically growing to make room for your circle. This idea sounds impossible to us. That's because in our world, everything expands into something else. Plants grow into the air, cities spread out into the countryside, ice spreads across the surface of the water. There is always somewhere for the expanding thing to go, always a boundary between what is expanding and what it is expanding into. But what if you were both the expanding picture and the paper it's expanding on? Scientists discovered this mind-bending truth by observing distant galaxies. Edwin Hubble noticed that galaxies farther away from us are moving away faster than those that are closer. At first glance, this makes it look as if we're sitting at the center of some cosmic explosion, everything flying outward into empty space while we stand in the middle. But the reality is much stranger and much more elegant. It isn't the galaxies themselves that are expanding, it's space itself. Galaxies aren't flying through space. The space between them is constantly stretching. Imagine dots drawn on the surface of a deflated balloon, but run the process in reverse. As the balloon inflates, the dots move away from each other across the surface without actually moving on their own. It's the surface itself that expands. From the point of view of any one dot, all the others seem to be moving away. No dot is special. No dot is at the center. Now replace the two-dimensional surface of that balloon with the three-dimensional space you live in. The universe isn't expanding into anything because there is no anything for it to expand into. It is constantly recreating the very stage on which expansion happens. This breaks our intuition so deeply that even the brightest scientists struggled with it for decades. Einstein himself initially rejected the idea, and yet this seemingly impossible expansion is happening right now, faster than you can comfortably imagine. Underneath this intuition-breaking idea that the universe is not expanding inside a container, but that space itself is expanding, lies solid evidence. Scientists reached this conclusion not through a philosophical guess, but by carefully reading the messages coming directly from the universe itself. That message was light, light that had been traveling through space for billions of years, and the secret it carried revealed the nature of cosmic expansion. Beyond any doubt, everything began in the early 20th century with Edwin Hubble's revolutionary observations using what was then the world's largest telescope. Hubble proved that the distant, hazy objects, known as spiral nebulae, were not part of the Milky Way at all, but were in fact separate galaxies, located millions of light years away. But his truly shocking discovery came when he analyzed their motion. Almost every galaxy he observed was moving away from us. Even stranger, the farther a galaxy was, the faster it seemed to recede. This perfect proportionality between distance and recession speed became known as Hubble's law. At first glance, it might give the false impression that we are at the center of the universe, standing at the heart of some enormous explosion with everything flying outward from us. But the deeper and far more elegant explanation was this: the same view would appear from any point in the universe. Because galaxies were not flying away through empty space, they were being carried apart as space itself expanded, just like raisins moving apart inside rising dough. No matter where you stand in the dough, all the raisins appear to drift away from you, and the more distant ones recede faster simply because there is more dough between you and them. While this analogy helps us imagine what's happening, it does not by itself prove that space is expanding. The true proof emerges when we understand how light is affected by this expansion. When a distant galaxy sends us a beam of light, that light begins its journey with a specific wavelength. Blue light, red light, ultraviolet light, each with its own signature. But as that light travels for billions of years through expanding space, something extraordinary happens. The very fabric of space stretches beneath it, and the wavelength of the light stretches along with it. It's like walking on a rubber band that someone is slowly pulling from the other side. Even if your steps stay the same, the ground beneath you elongates, making your journey longer than expected. Light experiences something similar, but since its speed cannot change, the stretching reveals itself as a shift to longer wavelengths. A photon that left its home galaxy as bright blue light arrives to us as weakened, redder light. This phenomenon is called cosmological redshift, and it is far more fundamental than the familiar Doppler effect of an ambulance siren lowering in pitch as it drives away. Light shifts to the red not because the galaxy is moving through space, but because space expanded during the photon's journey. Each individual wave of light is forced to stretch as the cosmic fabric beneath it expands. This is the most direct proof that space behaves as a physical entity with its own dynamics, independent of the objects it contains. And the scale of this effect is staggering. Light from the most distant galaxies we can observe has been stretched to nearly 40 times its original wavelength. That means the universe expanded by a factor of 40 during the light's journey. What began as intense ultraviolet radiation now reaches us as faint infrared warmth. This reveals not only that expansion is real, but that it has been a colossal, relentless force throughout cosmic history. This expansion is woven into the very structure of the universe, one of its most fundamental properties. Cosmological redshift shows, beyond doubt, that space is expanding over billions of light years and unimaginable distances. Yet, this immediately triggers another question in our minds. If space is expanding everywhere, why don't we feel it around us? Why aren't the walls in this room drifting apart? Why isn't the distance between you and the screen you're reading slowly increasing? The answer lies in the balance of forces that govern the universe. Though cosmic expansion is immense on large scales, it is extremely weak locally. Right now, that the space in this room truly is trying to expand. The gaps between the atoms that make up your body are trying to stretch. But opposing this gentle tendency are other forces that are trillions of times stronger. The electromagnetic force holds atoms together with ease, utterly overwhelming the push of expansion. Your molecules remain intact because their internal bonds dominate. Similarly, Earth's gravity binds you and everything around you to the planet. The sun's gravity binds the solar system. The collective gravity of the Milky Way binds hundreds of billions of stars into a single galactic structure. Within these domains, these forces completely cancel out the subtle push of expanding space. Expansion is like a faint current on a river. A strong swimmer, or in this case, gravity and electromagnetism, easily defeats it. But in the enormous voids between galaxies, the situation changes. In those vast stretches of darkness spanning millions of light years, there is no meaningful gravity or atomic force to hold space together. In those empty expanses, nothing resists the gentle current of expansion. There, space is free to stretch, carrying galaxies apart like raisins in rising dough. The raisins, the galaxies, do not expand because their internal forces are far stronger. But the dough between them, space, does. And that inevitably brings us back to the fundamental question we began our journey with. If expansion is an intrinsic property of space itself and only shows up where other forces are weak, then why does the question, what is the universe expanding into, collapse logically? Because that question ignores the fact that you are part of the dough. You're asking what the dough is rising inside of, but the one asking the question is also made of dough. Concepts like outside and into assume that an observer can stand outside the system they're observing. You can watch a balloon expand because you're outside the balloon. Your room provides an outside for the balloon. But when it comes to the universe, by definition, there is no outside. If there were, it too would be part of the universe. The universe is the sum total of everything that exists. So, when the universe expands, it isn't one thing moving into something else. It is the scale of the system itself changing according to its own internal dynamics. This is not just a word game or a philosophical trick. It is one of the deepest consequences of Einstein's general theory of relativity. The theory doesn't treat space and time as two separate things, but as a dynamic whole called space-time, the very fabric that makes up the universe. This fabric can be bent, curved, and yes, expanded by the matter and energy within it. Expansion is something this fabric does on its own, does not need an external container. So the question, what is the universe expanding into, is not a question without an answer. It's a question that is asked in the wrong way, like asking, what lies north of the North Pole? Or, what does the color blue sound like? These questions try to push concepts beyond the domain where they make sense and they fall apart. To understand cosmic expansion, we have to set our everyday intuitions aside and accept that reality may be far stranger and far more fascinating than anything we routinely experience. When we step outside at night and look up at the star-filled sky, we feel as if we're seeing the universe, as if the whole of reality is spread out above us like an infinite canvas. But this is one of the greatest tricks our mind plays on us. That scene we perceive as infinite is actually only a tiny fragment of the universe itself. In truth, we're seeing perhaps less than 4% of what exists. Without realizing it, we are trapped inside an invisible sphere. Its radius is about 46 billion light years. Beyond its boundary, more universe stretches on, billions more galaxies, trillions more stars, and perhaps even other versions of you reading these words. But we will never see any of it. No telescope humanity can build, no technology that could ever exist will let us look past that limit. This isn't a prison made of walls or barriers. It's an ultimate cosmic prison whose walls are made of time itself. To see how this trap works, we need to recall two basic facts about the universe. The speed of light is finite, and the age of the universe is finite. It takes time for light to travel. When we look at the sun, we see it as it was 8 minutes ago. When we look at Alpha Centauri, the nearest star system, we're looking 4 years into the past. When we look at one of the most distant objects visible to the naked eye, the Andromeda Galaxy, we're seeing it as it was 2.5 million years ago, before the human species even existed. The farther we look into space, the deeper we look into time. And this is exactly where the trap closes in around us. The universe is about 13.8 billion years old. That means the oldest light that can possibly reach us has been traveling for at most 13.8 billion years. If any galaxy is farther away from us than 13.8 billion light years in terms of light travel distance, its light simply hasn't had enough time to arrive. From our perspective, that galaxy might as well not exist. But wait, the trap is even tighter than that. We must remember that while that light was on its way to us, space itself was continuously expanding. The distant galaxy whose light we see today was much closer to us when it emitted that light billions of years ago. As light travels toward us over that immense span of time, the universe's expansion carries that galaxy far, far away, well beyond the 13.8 billion light-year limit. Today, a galaxy whose light set out 13.8 billion years ago and has just now reached us is actually sitting about 46 billion light-years away. That's what creates your cosmic prison cell. Everything beyond 46 billion light-years from Earth exists in what scientists call the unobservable universe. You can't see it, you can't detect it, you can't prove it's there. And yet logic and mathematics insist it must be. Imagine standing in a thick fog that limits your vision to 100 meters in every direction. Around you, there's a visible circle, but you know the world continues beyond the mist. The observable universe is your fog-limited circle. The real universe may well stretch on infinitely in every direction. And here comes the eerie, humbling number. If the universe truly is infinite, then your observable bubble contains exactly 0% of what really exists, 0. Because any finite number divided by infinity is 0. Everything we see, trillions of galaxies, trillions of stars, all that grandeur and immensity, could still be a zero-sized fraction of reality itself. This is one of the most humbling and unsettling lessons about our place in the cosmos. Everything we see is, in a sense, almost nothing. So what lies beyond the walls of this cosmic prison? Before we ask what's outside those walls, we have to understand what these walls are actually made of. The outer edge of the observable universe is not just empty darkness. On the contrary, that boundary is drawn by the oldest light the universe has ever produced. That light is still racing toward us right now at about 300,000 kilometers per second, carrying a message from the moment reality first became transparent. It has been traveling since long before Earth existed, long before our solar system formed, even before our galaxy, the Milky Way, settled into its present shape. This light began its journey when the universe was only about 380,000 years old. Back then, the cosmos was a seething plasma soup, so hot that even atoms couldn't form. Today, the ancient radiation we call the cosmic microwave background, CMB for short, is everywhere. On an old analog TV, when you flip between channels and see that static snow, about 1% of that fuzz comes from this primordial light. You are literally watching the afterglow of creation flicker on your screen. This radiation fills every cubic centimeter of space. It comes from all directions at once. It is the oldest thing the human eye, or our instruments, can possibly detect. What makes this discovery so profound is that this light marks the outer edge, the ultimate horizon of everything we can observe. Before that moment, roughly 380,000 years after the Big Bang, the universe was opaque. It was like trying to see inside the sun's surface. The early cosmos was like that everywhere light, photons, couldn't travel more than a few centimeters in that dense plasma of free electrons and protons. Every photon was immediately scattered or absorbed by charged particles. Then something miraculous happened. As the universe expanded, it cooled past a critical temperature. At that point, protons and electrons could finally combine to form the first hydrogen atoms. Suddenly, the cosmic fog lifted. The free charged particles that had been blocking light became trapped inside neutral atoms. The universe turned transparent. Light was finally free to travel through space without constant interruption. The first photons to escape that cosmic dawn are the very ones that reach our eyes and telescopes today as the cosmic microwave background. This moment, known as recombination, created the ultimate horizon. Anything before it is forever hidden from us. Whatever happened in those first 380,000 years will remain eternally out of reach. It's like trying to see through a solid brick wall that wraps around the entire early universe. The cosmic microwave background is that wall, and it marks the absolute limit of observation. But this horizon is not a static barrier. Every second, it moves. Light that has been traveling for 13.8 billion years, plus one more second, is reaching us right now. Our observable universe grows by 1 light second every second. That's roughly 25 billion more kilometers of reach every single day. But cosmic expansion makes this simple growth much more complicated. As our observable horizon expands, the true distance to the sources of that ancient light also keeps increasing because of the universe's expansion. A galaxy that emitted a photon 13.8 billion years ago is now sitting about 46 billion light years away from us. We're not seeing where it is, we're seeing where it was. This creates a strange situation. We are constantly seeing new regions of space for the first time, even as the sources of that light are steadily pulled farther away from us. It's like watching a movie of someone walking away, while the screen itself keeps stretching larger and larger. The cosmic microwave background shows us that in that early youth of the universe, aside from tiny temperature variations of just a few parts in a million, it was smoother than a sheet of glass. Those microscopic temperature ripples would eventually grow into everything: galaxies, stars, and us. But when we go beyond this oldest horizon in our imagination, when we mentally step behind that wall, what do we find there? Once we pass beyond the cosmic microwave background, the ultimate edge of what can be seen, we enter a realm where hard evidence ends and logical inference begins. What lies behind that wall? The simplest and perhaps most unsettling possibility is this: more of the same. Simply more of what we already see. That might sound boring, but in cosmology, it is actually one of the most shocking possibilities of all. If you could somehow teleport 47 billion light years away, just beyond our observable boundary, you would most likely find yourself in a region that looks very similar to this one. More galaxies, more stars, more planets, and perhaps more life. On the largest scales, the universe appears to have the property of being homogeneous. Homogeneous means uniform, the same everywhere, like a perfectly mixed cake batter. Every spoonful has the same ingredients in the same proportions. When we observe the cosmic microwave background radiation, we see evidence of this homogeneity. Those tiny temperature variations we detect are spread across the entire sky in a smooth and consistent pattern. That smoothness tells us something profound about what lies beyond our field of view. If our observable universe contains roughly 2 trillion galaxies, then a region of the same size just beyond our horizon should also contain roughly 2 trillion galaxies. And in the next region beyond that, another 2 trillion. This pattern continues forever, or at least far beyond anything we can truly grasp. This is where the idea becomes psychologically disturbing. If space is truly infinite and homogeneous, then every possible arrangement of matter within a given volume must occur somewhere. This isn't mystical thinking, it's a mathematical necessity. If you have infinite space and only a finite number of ways to arrange a finite number of particles, repetition becomes unavoidable. Imagine shuffling a deck of cards an infinite number of times. Sooner or later, you must get the exact same sequence again. The universe works similarly, except the cards are atoms. This means the following: there are other versions of you reading these exact words, not metaphorically, literally, in regions of space so far away that their light will never reach us. Quantum mechanics has arranged matter in every way it possibly can, including configurations that are identical to your current one. There are versions of you who decided to stop reading this sentence. Versions of you who were never born. Versions of you in which world history unfolded completely differently. But this assumption rests on the idea that the universe beyond our horizon looks like the one inside it. What if it doesn't? Recent observations hint that our local patch of the universe might be somewhat unusual compared to the rest. We seem to live in a cosmic void, a region with lower than average galaxy density. If that's true, then traveling beyond our observable horizon might take us into regions of space that are denser, with more galaxies, more black holes, more activity, or conversely, it might take us into regions that are almost completely empty. Some theoretical models suggest that cosmic inflation, the rapid expansion that occurred in the first fraction of a second of the universe, may have produced regions with radically different properties, pocket universes with different physical constants and different particle types, even completely different laws of physics. These pocket universes could exist just beyond what we can observe, operating under rules that would make our physics textbooks meaningless. Yet beneath all this speculation lies an even more fundamental question. What if the universe is not infinite? That raises a whole new set of unsettling questions. What lies beyond its edge? How can space itself have a boundary? What happens if you try to cross that edge? Questions like these, despite their conceptual difficulties, have led many scientists to favor models of an infinite universe. Because in an infinite universe, there is no outside. And that makes the question, what is the universe expanding into, meaningless from the start? Our current measurements show that the universe is either infinite or so large that any curvature is too small to detect. The simplest interpretation is that space extends infinitely in every direction, and that brings us back to the mind-bending idea we started with. Everything we see is, in fact, almost nothing. The notion of an infinite universe that is also expanding creates one of the most beautiful paradoxes in physics. Our minds immediately ask, how can you make infinity bigger? Mathematics tells us this should be impossible. Add anything to infinity, and you still have infinity. Multiply infinity by 2, and you still have infinity. You can't add to something that already includes everything. It feels like a logical dead end. And yet, when we point our telescopes at the sky, the reality is unambiguous. Space is expanding everywhere. The resolution of this paradox lies in redefining what we mean by expansion. When the universe expands, it doesn't mean it becomes more infinite or that new space is being added to infinity. It means the scale of space itself is increasing. To grasp this better, imagine an infinite sheet of graph paper where each square is 1 centimeter wide. This paper extends infinitely in all directions. Now imagine magically stretching the paper so that each square is now 2 centimeters wide. The paper is still infinite. It still has an infinite number of squares, but the distance between any two marked points has doubled. The sheet itself hasn't grown because it was already infinite. Only the scale has changed. That's exactly what happens during cosmic expansion. The universe doesn't become more infinite. The scale factor of space increases, causing all distances to grow in proportion. A galaxy that is 100 million light-years away today would have been 50 million light-years away when the universe's size was half of what it is now. The distance grew along with the scale of space. This leads to a disturbing but logically consistent conclusion. If the universe is infinite now, then it must also have been infinite at the moment of the Big Bang. That completely changes the picture in our minds. The Big Bang was not matter and energy exploding outward from a single point into empty space. It was an event in which an already infinite space, filled everywhere with immense energy, began to expand and cool all at once. Picture this. The Big Bang happened everywhere, throughout the entirety of infinite space, at the same time. There was no center, no edge, no outside. There was only an infinite space that suddenly began to expand and cool. Every point in the universe can claim to be the center of that expansion, because from every point of view, the expansion looks exactly the same. Right now, you're sitting at the center of your own personal Big Bang, just as a hypothetical observer in a galaxy billions of light years away, sitting at the center of theirs. This infinity perspective solves a few cosmic puzzles while creating new ones. For example, it explains why the universe looks the same in every direction from where we are. In an infinite and homogeneous space, every location is equivalent to any other. It also explains why we don't see any evidence of an edge or center, because there is no edge and no center to see. But it raises a deeply unsettling question. If the universe contains infinite matter and energy, how do we avoid infinite density? The answer lies in remembering that density is matter divided by volume. Even if both matter and volume are infinite, their ratio can still be finite. The universe can contain an infinite amount of matter spread across an infinite space and still maintain a specific average density, about 5 hydrogen atoms per cubic meter. Here's where the paradox becomes personal. In an infinite universe, every possible event will occur not just once, but an infinite number of times. Not only the other versions of you we mentioned earlier, but every possible story, every possible version of every story plays out somewhere in that vast expanse. Every tragedy, every victory, every moment of beauty, every act of cruelty. If that idea disturbs you, consider the alternative. A finite universe raises equally unsettling questions. What lies beyond its boundary? How can space itself have an edge? Questions like these have pushed many scientists toward preferring infinite models, and our current observations support the view that the universe is either infinite or so large that any curvature is too small to detect. This means that the expansion you observe is not creating new rooms, the way you might add new extensions to a house. It's simply stretching an already existing infinite fabric. If space is just stretching an infinite fabric, we're left with the question of what drives that stretching in the first place. What powers this relentless, all-pervading expansion? The answer may lie in one of the most mind-bending and counterintuitive facts about the universe. It is creating new space out of what looks like pure nothingness at an almost unimaginable rate. Every second, the volume of observable space increases by trillions upon trillions of cubic meters. That number is so huge that if you tried to count to it out loud, saying one number per second, you would need a time longer than the entire age of the universe by billions of times. And all of this new space emerges from something called the quantum vacuum. The quantum vacuum is not the quiet, empty nothingness we imagine. On the contrary, it is a seething sea of virtual particles popping into existence and annihilating each other on time scales shorter than the smallest measurable instant. This process, known as quantum fluctuation, fills every point in space with energy. Even in a perfect vacuum, this quantum activity never stops. Here's the mind-bending part. This vacuum energy has gravitational effects, but unlike normal matter, which pulls things together. Vacuum energy creates a kind of repulsive gravity. It pushes space apart, and this process feeds on itself. The more space you have, the more vacuum energy you have. The more vacuum energy you have, the faster space expands. The more space expands, the more room there is for new vacuum energy. This runaway process is known as inflation. A tiny fraction of the first second of the universe, inflation ran completely wild. Space expanded faster than light could ever hope to travel. This doesn't mean anything moved through space faster than light. It means that space itself grew faster than light could cross it. Imagine trying to walk on a treadmill that accelerates faster than you can run. No matter how hard you try, you can never get back to where you started. A region smaller than a proton ballooned to roughly the size of a basketball in a time shorter than a trillionth of a trillionth of a trillionth of a second. It sounds like science fiction, but quantum mechanics actually requires such a possibility. Heisenberg's uncertainty principle says that energy can be borrowed from the vacuum as long as it is paid back quickly enough. During inflation, the universe borrowed an enormous amount of energy to create new space and then used the expansion itself to repay that debt. It's like taking out a loan to buy a money printing machine, then using the printed money to pay off the loan. The process worked so well that it overshot its target. Inflation created far more space than was necessary to solve certain cosmological problems. Our entire observable universe is just one tiny patch, no more than a pinprick on this vastly inflated region. But the strangest part is that this process is still going on today. The current expansion is nowhere near as violent as inflation was, but it operates on similar principles. Dark energy, which makes up about 68% of everything, behaves almost exactly like vacuum energy. It uniformly fills space and generates a repulsive gravitational effect that accelerates the expansion. As the universe grows, more dark energy appears to fill the newly created space. This seems to violate everything our intuition tells us about the conservation of energy. Energy cannot be created or destroyed, yet the expansion appears to be constantly creating new dark energy. The resolution of this paradox lies in understanding that gravitational potential energy is negative. As space expands, matter becomes more spread out, and the gravitational binding energy, that negative energy, increases in magnitude. This growing reservoir of negative energy balances out the newly created positive dark energy. Even as the universe continuously creates new room, it maintains a perfect overall energy balance. This process appears likely to continue forever, or at least far longer than anything the human mind can truly grasp. Every moment that passes brings new space, new dark energy, and an ever faster expansion. The universe grows not because it needs a room to expand into, but because the expansion is constantly creating its own room. The idea that, in the very first moments, the universe grew from a region smaller than a proton to enormous scales in a time shorter than a blink by trillions of times is so fantastical, so deeply counter to our intuition, that without solid evidence, it would remain pure speculation. So what evidence do we have that this impossible seeming story really happened? Ironically, the answer was hidden in the static of old television screens. Part of that seemingly random noise carried the faint echo of the most violent event in cosmic history. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, working at Bell Labs, were trying to eliminate a stubborn background hiss in their antenna data. No matter what they did, the noise wouldn't go away. They cleaned pigeon droppings off the equipment, recalibrated their instruments, pointed the antenna at different parts of the sky. Yet the hiss persisted. That was because it wasn't coming from their gear or from Earth. It was the echo of creation itself. What Penzias and Wilson accidentally discovered was the cosmic microwave background radiation, the CMB. The afterglow of the Big Bang, stretched and cooled by 13.8 billion years of expansion. Their discovery earned them the Nobel Prize and provided the most direct evidence we have for an expanding universe. What makes this radiation so important is that it carries the signature of cosmic expansion literally imprinted in its wavelength. When this light first escaped the early universe, it corresponded to a bright, visible glow with a temperature of about 3,000 degrees Celsius. As space expanded, the wavelength of that light stretched along with it. What began as intense visible photons first shifted into infrared radiation, then into microwaves, and eventually into radio waves. Today, this ancient light reaches us with a temperature just 2.7 degrees above absolute zero. The cosmic microwave background radiation is astonishingly uniform, except for tiny fluctuations of a few parts in 100,000. And that uniformity is exactly what inflation theory predicts. Without inflation's rapid expansion, different regions of the universe wouldn't have had enough time to reach thermal equilibrium, and we would expect to see dramatic temperature differences across the sky. Instead, we observe an almost perfect smoothness. This tells us the universe was once incredibly small and tightly connected, then ironed out in every direction by a uniform expansion. But those tiny temperature variations tell an even more remarkable story. They represent quantum fluctuations stretched from subatomic scales to cosmic scales by inflation. Those microscopic density ripples in the early universe became the seeds that would eventually grow into galaxies, stars, and planets. Your very existence comes from a quantum uncertainty magnified by cosmic expansion. Advanced satellites like COBE and Planck have mapped these temperature variations with exquisite precision. The patterns they revealed match the predictions of inflation so well that cosmologists can now use this ancient light to measure the universe's fundamental properties. We can determine that, within measurement error, space is geometrically flat. We can calculate that ordinary matter makes up only about 5% of the total universe. We can pin down the expansion rate of the cosmos and its age with striking accuracy, all by studying that faint static. Yet the cosmic microwave background radiation reveals something even deeper about the expansion. This light shows us that everything we can see today was once compressed into a region about the size of a beach ball. Everything you can observe in the night sky, every galaxy our most powerful telescopes can detect, once occupied a volume smaller than what you could hold in your arms. This compression wasn't like cramming matter into a tiny box. Space itself was compressed. That beach ball didn't contain the early universe. That beach ball was the early universe. There was no outside, no surrounding emptiness, only that tightly packed region of space-time, which then began to expand into the cosmos we inhabit today. This is one of the most concrete answers we can give to the question, what is the universe expanding into? It wasn't expanding into anything. In the beginning, there simply was no place for the concept of outside to even make sense. The universe was both the stage and the actors at the same time. The fact that the universe is expanding was a cornerstone of cosmology for most of the 20th century. But there was a common assumption about its fate, that gravity would eventually win. All that matter, all those galaxies and stars, were expected to act like a kind of cosmic brake on the expansion. Over time, the expansion should have slowed down. The only debate among scientists was how strong that slowdown would be. Would the universe keep expanding forever, just more and more slowly? Or would it eventually stop and collapse back in on itself in a big crunch? In 1998, two separate teams of astronomers set out to measure that deceleration rate precisely. It was an ambitious project designed to answer one of cosmology's most fundamental questions. But what they found was not a slowdown at all. It was the exact opposite. The expansion of the universe wasn't decelerating, it was accelerating. That discovery won the Nobel Prize and completely upended our understanding of cosmic evolution. Suddenly, we realized that the ultimate fate of the universe is not governed by gravity pulling everything together, but by a mysterious, invisible force pushing everything apart. The key to this revolutionary discovery was a special kind of stellar explosion known as a Type Ia supernova. These supernovae occur when a white dwarf star steals matter from a companion star until it reaches a critical mass and detonates. Because that critical mass is always the same, the brightness of these explosions is also nearly the same. That makes them the most reliable standard candles in the universe, like identical cosmic light bulbs scattered across space. Since we know exactly how bright they should be, we can measure how bright they appear to us and calculate their distances with incredible precision. The basic physics is simple. The farther away something is, the dimmer it looks. The teams observed these explosions in galaxies billions of light years away. From each supernova's apparent brightness, they calculated its distance. At the same time, by measuring the redshift of the light, they determined how fast each galaxy was receding from us, and thus how much the universe had expanded while that light was traveling. The expectation was clear. Very distant supernovae, which exploded when the universe was younger and gravity was stronger relative to expansion, should appear brighter than a simple distance-velocity relation would predict. That would mean they were slightly closer than expected. But the data showed the exact opposite. The distant supernovae were dimmer than expected. There was only one possible conclusion. They were farther away than they should have been. As the light traveled toward us, the space between expanded far more than expected. At some point in the past, the expansion of the universe had stopped slowing down and had mysteriously begun to speed up. It was as if someone had lifted their foot off a cosmic brake pedal and pressed down on an invisible accelerator. Scientists named this mysterious force one that pushes space apart with increasing strength, dark energy, and it dominates everything in the universe. Dark energy makes up roughly 68% of the universe's total mass energy content. It outweighs all the ordinary matter that forms stars, galaxies, and planets by a ratio greater than 10:1. It even overshadows dark matter, the invisible skeleton that holds galaxies together. And yet, we have no idea what it is. It is an invisible, omnipresent force woven into the fabric of the cosmos, pushing everything apart. This discovery rewrote every scenario about the universe's fate and forced us to confront one of nature's deepest mysteries. What makes dark energy so strange is not only that we don't know what it is, but also how it behaves. It behaves fundamentally differently from anything else we know. Matter and radiation dilute as the universe expands, but dark energy does not. Its density stays constant even as space stretches. As the universe grows, it is as if new dark energy appears out of nothing to fill the newly created volume. It's like doubling the size of a room and having new air molecules magically appear so the air density stays the same. This means dark energy's total influence increases over time. In the early universe, when everything was much closer together, matter and radiation dominated because their densities were enormous. Dark energy existed then too, but it was negligible compared to the gravitational pull of all that concentrated matter. But as expansion continued, matter thinned out. Galaxies drifted apart and matter density fell. Dark energy, meanwhile, maintained the same density in every new patch of space, growing stronger and stronger by comparison. About 5 billion years ago, a turning point occurred. Dark energy's repulsive force surpassed the unifying pull of gravity. That was the moment the universe's expansion stopped slowing and began to accelerate. Strikingly, this transition happened around the same time our solar system was forming. Before that moment, expansion was slowing down because of gravity. After that, it began speeding up because of dark energy. We live in what cosmologists call the era of acceleration. With every passing day, dark energy becomes slightly more dominant. With every passing day, expansion speeds up just a little more. This acceleration is too subtle to notice on human timescales, but on cosmic timescales, it is dramatic. In the far future, dark energy will become so dominant that distant galaxies will begin receding from us faster than light. Not because they're moving faster than light, but because the space between us is expanding faster than light can cross it. From our perspective, those galaxies will disappear from our observable universe, like ships fading over a cosmic horizon. But what exactly is this invisible force controlling the fate of the universe? The leading candidate is vacuum energy, the quantum fluctuations filling every point of space. Quantum field theory predicts that empty space should contain an enormous amount of energy. But when physicists calculate how much energy the vacuum should contain, the result is 10 to the power of 120 times larger than what we observe. This is the worst, most embarrassing prediction in the history of physics. Such a colossal mismatch implies that either our understanding of quantum mechanics is fundamentally flawed, or some unknown mechanism cancels nearly all of the vacuum energy, leaving behind only the tiny amount that drives cosmic acceleration. Alternative theories suggest dark energy might be a new field, like the electromagnetic field, but with different properties. Others propose that gravity itself changes at cosmic scales in ways we do not yet understand. The truth is, we know as little about dark energy today as ancient humans knew about the nature of lightning. And yet, this mysterious force shapes the entire cosmic future and continues what may be the faint after echo of a far more dramatic expansion in the universe's earliest moments. Our search to understand this accelerating expansion leads back to one of the greatest minds in science, facing a contradiction within his own theory. In 1917, when Einstein completed general relativity, he realized that his equations predicted something troubling. The universe should either expand or contract. They did not allow for a static universe, but at the time, Einstein and everyone else believed the universe was eternal and unchanging. A dynamic, evolving universe sounded absurd. How could the whole cosmos be changing? Expanding into what? What would trigger such expansion? Believing that observational evidence, though incorrect at the time, supported a static universe, Einstein modified his equations. He added a new term, represented by the Greek letter lambda, which he called the cosmological constant. This term acted as a repulsive force that perfectly balanced gravity's pull. It allowed the universe to remain static despite containing matter, a delicate equilibrium. The cosmological constant represented the energy of empty space itself. Einstein imagined this vacuum energy as a gentle outward pressure that prevented gravitational collapse. For over a decade, this seemed like a reasonable solution. Then Edwin Hubble discovered that distant galaxies were receding from us. The universe was not static, it was expanding, exactly as Einstein's original equations had predicted. The observational evidence that convinced Einstein to add the cosmological constant had simply been wrong. Einstein quickly discarded the constant and called it his greatest blunder. Had he trusted the elegance of his original equations instead of flawed observations, he could have predicted cosmic expansion purely through theoretical reasoning decades before Hubble observed it. He could have been remembered as the scientist who foresaw the expanding universe. Instead, he invented a term he later regretted and spent years trying to remove it from physics. But the story didn't end there. In 1998, when astronomers discovered that expansion was accelerating, everything changed again. Something was pushing space apart with increasing force, exactly what Einstein's cosmological constant was designed to do. His mistake became a profound insight essential to understanding the universe. The accelerating expansion requires a form of dark energy that behaves precisely like Einstein's cosmological constant, an energy density that fills space uniformly and produces a gravitational repulsion. Current observations show that the cosmological constant is still the model that best fits the data. If this interpretation is correct, then Einstein's intuition about the energy of empty space was remarkably ahead of its time. He realized that the vacuum itself could possess energy and gravitational effects. Even though he added this idea to his equations for the wrong reasons, the idea itself was right. In our universe, the value of the cosmological constant is tiny, but not zero. Every cubic centimeter of empty space contains roughly 10 to the negative 10th joules of dark energy. This may seem negligible, but when multiplied by the enormous volume of the observable universe, it amounts to more energy than all the matter and radiation in existence. Einstein's supposedly unnecessary term now governs cosmic evolution. Yet the cosmological constant also brings a new problem, one Einstein never anticipated. If the acceleration is driven by vacuum energy, why is its value so small? Quantum field theory predicts that vacuum energy should be about 10 to the 120 power times larger than what we observe. This vacuum catastrophe is one of the deepest mysteries in physics. Solving it may require entirely new physics, far beyond what Einstein imagined. The irony is profound. Einstein added the cosmological constant to stop expansion, then abandoned it when expansion was discovered. Modern cosmology resurrected it to explain why the expansion is accelerating. The universe is racing irreversibly toward a cold and empty state. In that future, no process anywhere will be capable of generating usable energy again. This inevitable end, known as heat death, represents the ultimate victory of cosmic expansion over all other forces of nature. Driven by the repulsive power of dark energy, space will stretch matter and energy so thin that the universe will eventually become a uniform, lifeless void near absolute zero. The timeline of this cosmic finale is almost entirely beyond human comprehension. Within about 100 billion years, the last stars will burn through their nuclear fuel and fade into darkness. No new stars will form because expansion will have thinned matter so much that gravity can no longer gather material to create new stellar nurseries. The universe will enter what cosmologists call the degenerate era, a time ruled by cold stellar remnants, white dwarfs, neutron stars, and black holes. But this is only the beginning of the end. After not billions, not trillions, but around 10 to the power of 34 years, even protons are predicted to decay into lighter particles. The atoms that make up your body, the planets, and the stars will spontaneously fall apart. Matter, as we understand it, will cease to exist. The expanding void will contain only electrons, positrons, and photons. This number stretches human imagination. If the universe's current age were compressed into a single second, the proton decay era would last longer than a billion years. And yet, this unimaginable duration represents only a tiny slice of the universe's future. After about 10 to the power of 100 years, black holes will become the only significant sources of energy in the cosmos. Black holes evaporate through Hawking radiation, slowly converting their mass into particles and energy. The evaporation of stellar mass black holes takes longer than the current age of the universe. The supermassive black holes hiding at galactic centers will survive for roughly 10 to the power of 100 years. When the final black hole evaporates, the universe will reach perfect heat death. No temperature differences will remain. No chemical reactions will occur. No computation will be possible. No form of life will survive. The cosmos will settle into maximum entropy, a state of perfect equilibrium where nothing interesting can ever happen again. Given our current understanding of physics, this fate appears unavoidable. Dark energy accelerates expansion, spreading matter and energy over ever-increasing volumes. Unless dark energy somehow changes its behavior, expansion will continue forever, carrying the universe toward this cold, empty destiny. But expansion poses a more immediate threat to the far future. As space stretches faster, distant galaxies will vanish from our observable universe. They won't cease to exist. They will simply recede so quickly that their light will never reach us again. From our perspective, they will fade and disappear beyond the cosmic horizon. In about 150 billion years, only our local group of galaxies will remain visible. Future astronomers living in the Milky Way will see a universe consisting of only a few dozen galaxies surrounded by empty space. They will find no evidence of cosmic expansion because all expanding regions will be beyond their observable horizon. These future scientists will conclude that they live in a small, static universe. The cosmic microwave background, the clearest evidence of the Big Bang, will also disappear. Expansion will stretch this ancient radiation to wavelengths too long to detect. Future civilizations will lose the very signal that revealed our cosmic origins. They will inhabit a universe stripped of its own history. The slow, calm, almost meditative ending of heat death is only one possible fate. If dark energy turns out to be more violent than we expect, the cosmos may face a much quicker and far more catastrophic end. This scenario, known as the Big Rip, proposes that the universe will not only expand forever, but eventually tear itself apart from the inside out. Compared to the slow fading of heat death, the Big Rip is a sudden and violent annihilation. This nightmare scenario depends on a specific assumption about how dark energy behaves. If the density of dark energy remains constant over time, the universe slowly marches toward heat death. But what if dark energy is getting stronger over time? This theoretical form of dark energy, known as phantom energy, increases its density as space expands. It creates a self-feeding loop. Expansion creates more phantom energy. More phantom energy accelerates expansion further, and this continues without end. Eventually, the acceleration becomes so extreme that it overpowers all the other fundamental forces of nature. In this case, destruction follows a terrifying timeline. About 1 million years before the Big Rip, dark energy becomes strong enough to overcome the gravity holding galaxy clusters together. The massive gravitational bonds that bind thousands of galaxies snap. Galaxy clusters dissolve, and each galaxy drifts away into the deepening cosmic void, isolated forever. About 200 million years before the end, expansion begins tearing apart individual galaxies. Stars are ripped from their galactic homes and scattered into space. The majestic spiral arms of the Milky Way unravel. Andromeda is torn apart. Each galaxy becomes a collection of isolated stars racing away from one another as space expands faster than gravity can hold them together. 30 minutes before the Big Rip, expansion overpowers the gravitational bonds of solar systems. Earth is torn away from the sun. The moon drifts away from Earth. Every planet in every solar system suddenly finds itself alone in rapidly stretching space. Their parent stars vanish into darkness, leaving planets to warm only with their own internal heat. The final 30 minutes of existence become increasingly violent. 90 seconds before the end, expansion becomes strong enough to break molecular bonds. The atmospheric gases surrounding every planet disperse into space. Oceans boil instantly, not from heat, but because the space between water molecules expands faster than intermolecular forces can hold the liquid together. A trillionth of a second before the Big Rip, atomic nuclei fall apart. The incredibly strong nuclear force that binds protons and neutrons together finally loses to the relentless stretching of space. Every atomic nucleus in the universe spontaneously separates into individual protons and neutrons. The matter that forms stars, planets, and life returns to its most fundamental components. And at the moment of the Big Rip, even space and time themselves may be torn apart. Some models propose that space can only stretch a certain amount before the very concept of distance breaks down. The metric that defines lengths and time intervals becomes infinite. Causality collapses. The universe doesn't simply end, it becomes physically meaningless. Whether this nightmare scenario happens depends entirely on the true nature of dark energy. Current observations show that dark energy has remained roughly constant throughout cosmic history, pushing us toward heat death rather than a Big Rip. but the data is not yet precise enough to rule out slow changes. Future measurements of distant supernovae and other cosmic distance markers will determine whether dark energy is growing stronger with time. If it is, we will be able to calculate exactly when the Big Rip will occur. Some estimates place this end roughly 22 billion years in the future, but this is only one model. The universe's final act remains an unwritten script. Einstein showed us that space and time are not separate things, but a unified fabric he called space-time. This fabric is the foundation of the universe, and when you stretch one part of a fabric, it is impossible not to affect the other parts. As cosmic expansion pulls space apart, it also stretches the flow of time everywhere in the universe. This is not just theoretical physics. It is a measurable reality that changes everything about how the universe ages. Imagine observing a distant galaxy through a telescope. Because of expansion, that galaxy appears to be receding from you. But here's what defies intuition. Events in that galaxy appear to unfold in slow motion compared to events in a nearby galaxy. A type Ia supernova that brightens and fades in 3 weeks in a close galaxy appears to last much longer when observed in a distant, rapidly receding galaxy. This does not mean time itself runs more slowly in that galaxy. Instead, it is caused by what happens to the information as light travels to us over billions of years. The light pulses carrying information about those events pass through expanding space. During this journey, not only does the wavelength stretch, but so do the time intervals between light pulses. The universe literally stretches time. In regions of space that are receding from us at high relative speeds, time appears to flow more slowly. The numbers demonstrating this effect are astonishing. Light from galaxies at the edge of the observable universe shows a redshift of about 10. That means, when this light was emitted, those galaxies were moving away from us at roughly 90% of the speed of light. As a result, events in those galaxies appeared 10 times slower than similar events happening here. This creates a bizarre situation where time depends on where you are. From our perspective, the universe is 13.8 billion years old. But if you could observe our region of space from one of those distant, rapidly receding galaxies, our cosmic neighborhood would look much younger. Time itself has been stretched by expansion. This temporal stretching reveals a profound truth about cosmic evolution. The early universe didn't just contain compressed space, it contained compressed time. Processes that take billions of years today happened far more quickly in that dense early cosmos. The formation of the first stars, the first galaxies, and the first black holes all occurred in a universe where time flowed differently than it does now. But expansion changes not only the rate of time's flow, it also alters the very concept of simultaneity across cosmic distances. Simultaneity is obvious in everyday experience. If two events happen at the same time, then they have happened at the same time everywhere. But relativity and cosmic expansion destroy this assumption. Events that appear simultaneous to you occur at different times for observers in distant galaxies. There is no universal now that applies everywhere in the universe. This collapse of simultaneity makes the question, what is the universe doing right now, meaningless on cosmic scales? Different observers define the present differently. The present moment is not universal, it is local. Your now is valid only at your own point in space-time. As expansion accelerates, these temporal effects become even more dramatic. The influence of dark energy grows stronger over time, stretching space even faster. This acceleration also speeds up the stretching of time. Future civilizations in our galaxy, when they observe distant galaxies, will see far more extreme time dilation effects. Eventually, expansion will stretch time so much that distant universes will appear completely frozen. Their light will continue reaching us, but the story carried by that light will seem trapped in a single frame, unfolding in eternal slow motion. This is the deepest evidence of how strange and flexible the fabric of the universe can be, far beyond the limits of our intuition. The universe's 13.8 billion year expansion history is astonishing on its own, but the most dramatic, violent, and important chapter of this story happened in an unimaginably tiny fraction of the first second. During a period known as cosmic inflation, the universe expanded far more rapidly than it has in all the billions of years since. It was an instantaneous, extremely intense burst of growth, stretching the fabric of space-time, smoothing it, and planting the seeds of everything we see today. This process occurred within the first trillionth of a trillionth of a trillionth of a second after the Big Bang. Grasping the brevity of that interval is nearly impossible. During this instantaneous burst, space was stretched so violently that regions of the universe permanently lost contact with one another. Points that were once close enough to exchange light signals were suddenly separated by distances light could never hope to cross. The universe had broken its own speed limit. This may sound contradictory. Physics tells us nothing can move through space faster than light. That is true. But during inflation, space itself expanded faster than light. This does not violate the rule, because the rule applies only to motion within space. There is no limit to how fast space itself can expand. It's like a balloon on which two ants are standing suddenly inflating at an extreme rate. No matter how fast the ants walk, they will never reach each other. The surface expands faster than they can move. This is exactly what happened to the early universe. The numbers that describe this expansion push the limits of human imagination. Inflation increased the size of the universe by at least 10 to the 26th power times. That's like a grain of sand suddenly becoming larger than the observable universe. And this expansion happened in an impossibly short time, about 10 to the negative 35 seconds. For perspective, light travels about 30 centimeters in a nanosecond. During inflation, the universe expanded by more than 20 orders of magnitude in a time so short that light could not even cross the width of a proton. The energy that drove this unbelievable expansion came from a hypothetical quantum field called the inflaton field. Unlike other quantum fields, the inflaton became trapped in a high-energy state known as the false vacuum. This created a temporary form of dark energy far stronger than anything observed today. While trapped in this false vacuum, the inflaton triggered exponential expansion. Exponential growth starts slowly but accelerates explosively. If you could fold a sheet of paper 42 times, its thickness would reach from Earth to the Moon. The universe underwent a similar but vastly more extreme process. During inflation, space doubled in size in every tiny fraction of a moment, then doubled again, then doubled again. This stretched the fabric of the universe so intensely that it smoothed out every wrinkle or imperfection imaginable. While this solved several major problems in cosmology, it also created new ones. For example, it explains why the cosmic microwave background radiation looks so uniform across the sky. Without inflation's rapid expansion, there is no reason regions of the universe now separated by such great distances should have the same temperature. Inflation acted like a cosmic iron, flattening everything. It also explains why space appears geometrically flat. Even if the universe started with noticeable curvature, inflation stretched that curvature so much that any remaining bending became undetectable, like inflating a basketball until its surface appears perfectly flat from your tiny vantage point. But the deepest consequence of inflation lies in its relationship with quantum mechanics. While smoothing and flattening the universe were already profound outcomes, inflation's most astonishing legacy is that it took the ghostly uncertainty of the quantum world and amplified it into a concrete, large-scale cosmic reality. During inflation, quantum fluctuations in the inflating field were stretched from subatomic scales to intergalactic distances. These tiny variations in early universe energy density became the seeds that would eventually grow into galaxies, stars, and planets. To understand this idea better, we must recall the nature of the quantum world. On the smallest scales, the universe is not calm or smooth. It is a boiling sea of virtual particles and energy fluctuations that constantly pop in and out of existence. This is an inevitable state of uncertainty known as quantum foam. Under normal circumstances, these fluctuations are so tiny and so short-lived that they have no effect on our large-scale world. But inflation changed the rules of the game. The extremely violent expansion of the universe in its earliest moments grabbed these microscopic quantum fluctuations and stretched them to unimaginable sizes along with space itself. An energy fluctuation that once occurred in a region smaller than the width of a proton became, within fractions of a second, a structure thousands of light years across. When inflation ended, these fluctuations were frozen into the fabric of the universe as permanent imprints. These imprints can still be seen today as tiny temperature differences in the cosmic microwave background, the universe's first map. Some regions are slightly hotter and therefore slightly denser by only 1 part in a million. Others are slightly cooler and slightly less dense. This temperature map is the baby picture of the universe, and it is a portrait of quantum fluctuations magnified by inflation. Once these initial seeds were planted, gravity took over. Regions that were slightly denser exerted slightly more gravitational pull on the matter around them. Over millions and hundreds of millions of years, these regions slowly but steadily attracted more matter. Dense regions became denser. Less dense regions became emptier. This was the formation of the universe's colossal structure known as the cosmic web. The denser regions became the bright filaments and nodes where galaxies and galaxy clusters formed. The emptier regions turned into vast cosmic voids between them. This carries an extraordinarily deep meaning. The Milky Way galaxy you live in, the sun that warms your planet, and the atoms in your body owe their existence to a random quantum event in the universe's earliest moments. You are a descendant of quantum foam. If inflation had not magnified those first quantum uncertainties to such vast scales, the universe would have remained perfectly smooth with no density differences for gravity to latch onto. No structures would have formed. The universe would have stayed forever as a uniform, dull, lifeless cloud of gas. But inflation also raises a disturbing possibility. If it happened once, could it happen again. The same quantum fields that drove primordial inflation may still exist, waiting for the right conditions to trigger a new period of exponential expansion. This could happen here, now, without any warning. A new inflation bubble could nucleate anywhere in space, expanding outward at the speed of light and destroying everything in its path. Inside this bubble, new laws of physics would apply. Our atoms would disintegrate, our laws of nature would stop working. We would never see it coming because it would expand faster than the light reaching us. This frightening possibility pales in comparison to the most mind-bending implication of inflation. What if our universe is just one bubble in an infinite sea of expanding realities? This idea takes us from the boundaries of science into the dizzying realm of the multiverse hypothesis. The theory of cosmic inflation not only explains the origin of our universe, but also brings us to the doorstep of a far larger, far more astonishing possibility: the multiverse. Although it sounds like science fiction, this idea is actually one of the most natural and logical consequences of inflation theory. If inflation happened once, quantum mechanics suggests it must be happening constantly across a larger arena known as the multiverse. According to this scenario, our universe is just one bubble among countless others in an endless, foamy sea. In a model known as eternal inflation, random quantum fluctuations can trigger new periods of inflation anywhere at any time. Each period creates a bubble universe of its own, expanding, cooling, and potentially developing its own galaxies, stars, and planets. This idea changes the definition of the word universe. Our universe is everything that arose from our Big Bang and obeys our laws of physics. But this may not be the only reality that exists. What makes this possibility so unsettling is that each bubble universe could have completely different physical laws. The strength of gravity could be different. The mass of electrons could vary. The number of spatial dimensions might not be 3. Most of these universes would be unimaginably alien and hostile to life. In some bubbles, gravity might be so strong that stars collapse instantly into black holes. In others, gravity might be so weak that matter could never come together to form structures. Some universes might lack the electromagnetic force entirely, making chemistry impossible. Others could remain in an eternal inflation state forever, never allowing atoms to form. The vast majority of bubble universes would be sterile and lifeless. But in an infinite multiverse, even the most improbable possibilities must occur somewhere. No matter how unlikely our particular combination of physical constants might seem, an infinite number of bubbles means an infinite number of chances for those constants to align perfectly for life. We exist in a habitable bubble, not because we are special, but because we can only exist in a habitable bubble. This reasoning, known as the anthropic principle, explains why our universe appears so finely tuned for life. We do not live in a universe designed for us. We live in the rare kind of universe where beings like us could evolve to ask such questions. But the multiverse concept brings deep philosophical problems as well. If there are infinite universes, then every event happens somewhere. Every decision you do not make is made by another version of you in another bubble. Every tragedy you avoid happens to another version of you somewhere else. Every dream you never reach is achieved by another you in a different reality. The multiverse contains infinite copies of everyone experiencing everything everywhere. This infinite repetition renders the concept of uniqueness meaningless. If you have infinite versions of yourself, then you are not unique. If every possible choice is made by some version of you, then your choices lose significance. If there are infinitely many similar universes beside yours, then your universe is not special. Yet the multiverse remains unobservable. By definition, other bubble universes lie beyond our cosmic horizon. Their light can never reach us. Their gravitational effects can never influence us. We can never prove their existence or determine their properties. The multiverse concept makes predictions that cannot be tested. This bothers many scientists who argue that untestable theories are not science. However, the mathematics of inflation strongly suggests eternal inflation and bubble nucleation. The same quantum field equations that explain the early expansion of our universe also predict continued expansion and bubble formation in a larger multiverse. If we accept inflation, we may have to accept its consequences as well. Recent observations have begun testing inflation's predictions with increasing precision. The cosmic microwave background contains subtle patterns that match inflation theory remarkably well. These observations strengthen confidence in inflation while indirectly supporting the concept of the multiverse. Perhaps we are living inside the best evidence for infinite other worlds. The expansion of the universe not only carries secrets about its past, but also signals an unavoidable scenario about its future. Driven by the repulsive force of dark energy, this accelerating expansion is slowly but inexorably pushing the cosmos toward an ultimate state of stillness and emptiness, known as heat death. This is not a fiery destruction, but a calm and melancholic ending where all motion, all energy, and all complexity slowly fade into eternal silence. The timeline of this cosmic finale stretches across scales that challenge the limits of human imagination. Over the next roughly 100 billion years, the last stars in the universe will exhaust their fuel. Those brilliant beacons that once illuminated the sky will dim one by one, turning into cold, dead remnants. No new stars will form because expansion will have thinned out matter so much that gravity can no longer gather gas and dust to spark new stellar births. The universe will enter an era dominated by white dwarfs, neutron stars, and black holes, a quiet reign known as the degenerate era. This will be a long night in which the lights of the cosmos are extinguished. But this is only the beginning of the end. After not billions, but an unimaginable span of about 10 to the 34th power years, even the fundamental building blocks of matter will lose their battle for existence. Protons, the particles that form the heart of atomic nuclei, are predicted to slowly decay into lighter particles. The atoms that make up your body, the planets, and the once shining stars will disintegrate on their own. Matter, as we know it, will slowly evaporate. What remains drifting in the ever-expanding void will be only fundamental particles such as electrons, positrons, and photons. Trying to comprehend this timescale induces a kind of mental vertigo. If you compressed the universe's 13.8 billion year history since the Big Bang into a single second, the era of proton decay would last longer than a billion trillion years. Even this staggering stretch of time represents only a small slice of the universe's future. After this era, for roughly 10 to the 100th power years, the only meaningful structures left in the cosmos will be black holes. They will drift silently through space as the final monuments of the once magnificent galaxies and stars. But even their fate is not eternal. As Stephen Hawking showed, black holes slowly evaporate through a process called Hawking radiation, converting their mass into particles and energy. For a stellar mass black hole, complete evaporation takes far longer than the current age of the universe. The gigantic supermassive black holes lurking in galactic centers will resist evaporation for up to 10 to the 100th power years. And finally, when the last black hole emits its final photon and evaporates, the universe will reach its ultimate and perfect heat death. No temperature differences will remain anywhere. Without temperature differences, there is no flow of energy. Without energy flow, no work can be done. No chemical reactions become possible. No computation can occur. No form of life, however exotic, can survive. The cosmos will have reached maximum entropy, an eternal state of uniformity and disorder. A state in which nothing interesting can ever happen again. The universe will become a silent, featureless, eternal void. This fate appears unavoidable given our current understanding of physics and the assumption that dark energy remains constant. Expansion is an unstoppable process, carrying the universe toward this cold, empty, tranquil end. It is less an explosion than a long exhale, the universe taking its final breath and falling into an eternal sleep. But the infinitely distant inevitability of heat death is not the only consequence of expansion. Expansion does not merely stretch the fabric of space, it also stretches the fabric of time that is woven together with it. As Einstein showed us, space and time are not separate entities. They form a single unified whole that bends together, ripples together, and expands together, a structure he called space-time. This has deep and strange effects on how the universe ages and how we perceive it. We see this effect most clearly when we observe distant galaxies. Because of expansion, events in a galaxy that is rapidly receding from us appear to unfold in slow motion from our frame of reference. This phenomenon is known as cosmological time dilation. For example, a supernova in a nearby galaxy that reaches peak brightness and fades within 3 weeks may appear to take weeks or even months when observed in a galaxy billions of light years away that is rapidly receding. This does not mean the clocks in that galaxy are actually running slower. For an observer in that galaxy, everything proceeds normally. The effect comes from what happens to the information, the light, on its way to us. The light carrying those events travels through expanding space for billions of years. This expansion doesn't just stretch the wavelength of the light into the red, it also stretches the temporal information encoded in those waves, the rhythm of the events themselves. The intervals between light pulses grow longer. The universe, quite literally, stretches time itself like a rubber band. This temporal stretching gives us an important clue about the nature of cosmic evolution. The early universe did not only contain compressed space, it also contained compressed time. Processes that take billions of years today happened much faster in that dense early cosmos. The formation of the first stars, the first galaxies, and the first black holes all unfolded in a universe where time flowed at a different rhythm. This is a critical detail for understanding cosmic evolution, but expansion's effect on time does not stop at changing its flow rate. So makes the very concept of simultaneity meaningless on cosmic scales. In everyday life, if two events happen at the same time, they happen at the same time for everyone. But relativity and cosmic expansion break this intuitive assumption. Events that look simultaneous to you may occur at completely different times for an observer in a distant galaxy. There is no universal now that everyone across the universe can agree on. This means that when we ask, "What is the universe doing right now?" we are actually asking a meaningless question. Now is only local. It is valid only at your space-time location. For a galaxy billions of light years away, now may be nothing like your now. As expansion accelerates, these temporal effects become even more dramatic. As dark energy grows stronger, space stretches faster, and this accelerates the stretching of time as well. Future civilizations in our galaxy, looking at distant galaxies, will observe time dilation far more extreme than what we see today. Eventually, expansion will stretch time so much that events in distant galaxies will appear completely frozen from our perspective. Light from those galaxies will still reach us, but the story it carries will look stuck in a single frame, unfolding in infinite slow motion. This is one of the deepest proofs of how strange and flexible the fabric of the universe can be, far beyond anything our daily experience prepares us for. Time is not a fixed, universal metronome. It is a dynamic phenomenon that stretches, bends, and flows differently, depending on cosmic expansion. The accelerating expansion of the universe not only carries everything toward a cold, distant ending, it also creates a more subtle effect. The universe is slowly erasing the evidence of its own past. Billions of years from now, future civilizations in the Milky Way will look out at a universe completely different from the one we see, and deceptively simple. They will live in a cosmic age where they will reach entirely wrong conclusions about the history of the universe. The reason is that dark energy is pushing distant galaxies away from us at an ever-increasing rate. About 150 billion years from now, all galaxies outside our local group will have crossed beyond the cosmic horizon. Their light will never reach us again, because the expansion of space between us will outpace the speed at which their light travels. From the perspective of future observers, those billions of galaxies will simply fade away and vanish. What will scientists of that distant era see when they look at the sky? They will observe a universe with only a few dozen galaxies, surrounded by what looks like endless empty space. By then, the Milky Way, Andromeda, and our local neighbors will have merged under gravity into a giant elliptical galaxy. This isolated island universe will appear to them as the entire cosmos. The cosmic microwave background, the strongest evidence for the Big Bang, will also have disappeared. Expansion will stretch this ancient radiation to wavelengths longer than the observable universe itself. Even the best future instruments will detect nothing. Without the microwave background, future cosmologists will lack the key evidence that the universe began hot and dense. The redshift distance relation, which first revealed cosmic expansion to us, will also become unmeasurable. With no distant galaxies to observe, future astronomers will never discover Hubble's law. They will have no way to detect that space is stretching. Their universe will appear completely static. Those future scientists may develop entirely different cosmological theories. They may conclude that their lone giant galaxy has always existed, unchanged, in an infinite and eternal void. Their cosmos may never even occur to them as a place that was once filled with billions of galaxies rushing away from each other because of expansion. They will live in a universe stripped of its own history and its own origins. But this loss of cosmic perspective goes even deeper. Future observers will also lose access to the laws of physics that governed the early evolution of the universe. The nuclear processes that forged the first elements will have ended billions of years earlier. Evidence of Big Bang nucleosynthesis will survive only as faint traces, barely readable in the chemical makeup of ancient stars. These future civilizations will face a deep epistemological crisis, a crisis of knowledge. They may be just as intelligent and technologically capable as modern humans, yet they will be looking at a universe that offers them very few clues about its true nature. Their scientific methods may work perfectly, but will lead them to wrong conclusions about reality, and this inevitably raises disturbing questions about our own cosmic knowledge. Are we, too, being misled simply because we happen to observe the universe in a particular era? Are we missing critical evidence that was visible to earlier observers but has already faded away and become undetectable by the time we exist? Perhaps civilizations that emerged not long after the Big Bang were able to see phenomena that will remain forever hidden from us. This is one of the great ironies of expansion. On the one hand, it creates the dynamic stage that allows complex structures, like galaxies, planets, and life to appear, making the universe interesting. On the other hand, that same expansion systematically erases the evidence of its own past, making the universe incomprehensible to its future inhabitants. Expansion builds the stage for existence, while slowly burning all the notes about how that stage was built. It means the universe gives us only a limited time window to truly understand its story, and by sheer luck, we are alive while that window is still open. At the end of our journey, we return to that first question echoing in the back of our minds. What is the universe expanding into? We have seen that this question is like asking what lies north of the North Pole, a logically flawed question that pushes our concepts beyond their valid range. But beyond this logical answer lies a deeper, more intuitive truth. Once we understand it, the question itself changes, and our relationship with the universe is reshaped. When we ask what the universe is expanding into, we are making a seemingly reasonable but actually impossible assumption that expansion needs some pre-existing room to grow into, just like a balloon needs air around it, or a city needs countryside to spread into. But the universe is not like a balloon. The universe is space itself. When space expands, it doesn't grow into something else. As it grows, it creates the very idea of something else. There is no outside, because the universe is what gives the word outside its meaning in the first place. This is not a limitation of human language or a failure of scientific imagination. It is a fundamental feature of reality. Before expansion, concepts like inside and outside simply do not exist. Expansion doesn't just create more room, it creates the very logical framework in which spatial relationships make sense. The universe is not expanding into something. As it expands, it also brings into existence the very notion of anything at all. Asking what the first cause's cause is, or what contains the container of everything, is the same kind of mistake. The question assumes categories that only make sense after the thing you're asking about already exists. The universe doesn't grow by pushing into not universe. It grows by becoming more universe. This realization transforms our understanding of cosmic expansion from a mere mechanical process into something far deeper. Expansion is not just the universe getting bigger, it is reality creating itself out of nothing. Every cubic centimeter of new space that comes into existence opens up new possibilities for matter, energy, structure, and complexity. The universe is not expanding toward a fixed destination, it is expanding toward the infinite space of what could be. We are not passengers on some cosmic vehicle heading toward a goal. We are part of the process by which reality creates itself. Our consciousness, our questions, our desperate need to understand what the universe is expanding into. These are all expressions of the universe beginning to know itself. The expansion we observe is not separate from us. We are that expansion. We are space, time, matter, and energy arranged in patterns complex enough to ask questions about their own existence. When we finally recognize that the question, what is the universe expanding into, is flawed at its core, the paradox of cosmic expansion fades and is replaced by an even deeper mystery. If the universe is creating its own space and time, if it serves as both its own stage and its own audience, then what we call existence may be far stranger than any science fiction story. Perhaps we live inside a process with no beginning and no end, no inside and no outside, self-existing and self-sustaining. And perhaps this process has no purpose beyond the sheer fact of its own astonishing unfolding. The universe expands not into something else, but into more of itself, opening up an endless space of possibilities. Among those possibilities is this one: beings like us, able to look at all of this impossible and beautiful process with awe. The question, what is the universe expanding into, has taken us on a journey through inflation and dark energy, through multiverses and quantum foam, all the way to the beginning and the end of time. But the deepest answer may have been in front of us all along. The universe is expanding into mystery, into curiosity, into more questions, more discoveries, into those moments when we feel we are part of something vastly greater than ourselves, and yet intimately connected to even our smallest thoughts. We are the universe in the form that asks, what am I expanding into? We are expansion in the form that asks, where am I going? We are space and time waking up to their own existence and marveling at the endless creativity of the process that gave rise to us. And in that realization, the question stops being a puzzle that needs to be solved. It turns into a celebration of the sheer impossibility of existence itself. Expansion is not motion toward a goal. It is the rhythm of being. With every moment, the universe isn't just getting bigger, it is becoming more itself. And we are both witnesses to and a part of that becoming. So, at this point, let's loosen our grip on the questions a little. Right now, maybe you're in a dark room. Maybe your eyes are closed, just listening to my voice and to the galaxies slowly drifting away in your mind. As the universe continues to expand, your thoughts can gently relax as well. Accepting that there are questions we cannot answer is, in a strange way, calming. We don't have to know everything. The simple fact that we exist here in this moment is already a miracle on its own. Maybe what really matters is not where the universe is expanding to, but what is expanding inside you as you listen to this story. Your curiosity, your sense of wonder, your search for meaning. Right now, as a rare piece of the universe that can think about itself. You are both a witness to this story and part of its continuation. If your eyelids are getting heavy, let your thoughts slip gently into the background, like the faint light from distant galaxies. Let the rhythm of your breathing fall into step with the calm heartbeat of cosmic expansion. If you enjoy these calm, deep, and mysterious journeys, if you'd like to keep exploring the secrets of our world and the universe with me, in this thin space between sleep and wakefulness, you might consider liking this video and subscribing to the channel. That way, when the next journey into mystery begins, we'll be here together. In the comments, there's something I'd love to hear from you. Which cosmic question occupies your mind the most? The end of the universe, its beginning, or the question, why is there something rather than nothing? You can write your answer while you're awake, and if you like, you can come back later, reopen this video, and simply listen to it as you fall asleep. Now, as the universe continues its quiet expansion, you too can slowly move toward a deep sleep. Thank you for staying with me all the way to this point. Until we meet again on the next journey.